Welcome back engineers, we are discussing common techniques and algorithms in system design, and in this video let's have a demo about LSM trees. I hope you're ready. Let's get started. So before we get into the demo, quick recap about what are LSM trees. So we discussed this in the last video. LSM tree is not a single data structure, it is an ecosystem of multiple data structures which are working really well together to create an efficient search system, especially when there are write heavy systems, right? So let's quickly recap how insert and read works. So in LSM trees concept, there are some things that are happening on the disk, there are some things that are happening in memory, right? So this is the write life cycle. So whenever we are writing something to LSM tree, first we are writing to a log, because we can use this for disaster recovery, and then we are putting stuff in memory, which is in MemTable. MemTable can be any balance search tree, right? So we are putting this in memory, so whenever we are reading from it, first we will look through this table, this MemTable, otherwise we'll fall back to disk, right? So we are here. So when this MemTable is full, we will translate all the content into a sorted string table, and then we have a concept of compaction here. When the sorted string table is full, it is going to merge itself into a larger sorted string table, and we can maintain multiple levels like this. So if there are two SSTables in level 0, when the threshold is met, let's say our threshold is 2, both of these will be merged into a larger table. And then when these two tables are filled in level 1, we go to level 2 and so on, right? This is a concept of compaction, right? So we are writing to a log, we're writing to a MemTable in memory, and then when the MemTable is full, we are translating to disk, and then we are maintaining stuff in disk, right? Now let's look at the read lifecycle. So while reading, we're going to look at MemTable first for the existing key. If it's available, we return from the MemTable. If it is not found, we're going to go to the disk where there are SSTables, and if we will try to search in the SSTables, because it is a sorted SSTable, we're going to use binary search there. We can also implement Bloom filter as an additional optimization, because we are essentially checking for one particular key in a long list of strings, right? So that's how read lifecycle works, right? Let's do a demo about all this. So this is our UI. So we're going to see the creation of the logs, the SSTables, the compaction SSTables in this demo. So let me take you through the demo first, and then we'll see the code, right? So in the backend, I have just my server running, and let me remove the log as well so that we'll start fresh. Okay, let's say there is nothing, no files created as of now, and I can start inserting stuff into my MemTable, right? Let's say I'm entering key value pairs. Let's say my key is 1, value is A. I'm putting it into my MemTable, right? This is in memory right now, and if we go back, we should see a log here. Okay, we see a log here. This is having the value key 1 and value A, right? So when do we fill the MemTable? So I have defined a threshold of having 2 inside my MemTable. So when I'm adding a third key into my MemTable, I want to flush it down to the SSTable. So when I'm adding the second key, let's say my second key is 2B. So what's happening here is my wall.log, which is my write-ahead log, this has been cleared now, and the data is transferred to SSTable. So if you look at the SSTable log, we now have 2 things, key 1, value 2, right? And then this is also my Bloom filter for additional optimization, which we'll use in getting a key, right? So this is how we can insert stuff. So we can repeat the process. Let's say my key is 3, value is B, key is 4, value is D, and so on. So now I have created the second SSTable, right? Because my threshold for keeping stuff in MemTable is 2, right? So I have 2 SSTables now, and my threshold for compaction is 4 SSTables. So if I create 2 more SSTables, they will combine into one larger SSTable. So let's do that. So let me add keys here. So let me add in a different order so that we can see that the table itself is sorted. Right now I've been adding in a sorted order myself, but let me jumble the order. Let's say I'm adding 6 first, 6F and then 5E, right? So we have already sorted in the SSTable. We have 5 and 6. So if you look at it, we'll have a third SSTable which will have 5 and 6. Already it is sorted, right? And let's add a couple more. 7G, 8H, right? Now, because I have kept the threshold of 4 SSTables, all of them have been combined into one large SSTable, and the earlier tables have been removed, So if you look at it, all the earlier logs are gone now. We only have one log with 8 values, right? So this is how the LSM tree write lifecycle works, right? Now let's see how read lifecycle works. So let's say I'm trying to get the value 2. I'm getting the value B. My key is 2 and my value is B. So what is happening here? First, I will try to look for something in the MemTable. If it is not found, I will try to go to SSTable. In SSTable, I have a Bloom filter optimization. So if it's found in the Bloom filter, then we go to the SSTable and then we get the actual value, right? So let me add a couple more. Let's say I'm adding the key 9 with value I, right? Now my value is in MemTable, but not in my SSTable. So if I want to get 9, it is getting me the value I, but that is coming from the MemTable. And when I request for something that is not there anywhere, let's say I'm requesting for 10, I get the value null because it's not there anywhere in my entire LSM tree structure, right? So how did it find it? First, it is looking for the MemTable. If it is not found, it's going to the Bloom filter. Bloom filter says it's definitely not there, so we'll return from there. If there is a maybe yes from the Bloom filter, maybe for key 6, we go to the SSTable and then we find 6 and then we return the value F, right? Similarly, we can also delete stuff. Let's say I'm trying to delete, let's say 7, okay? Now in my second SSTable, we have 7 delete and 9 as I. Now if I try to get 7, we get null because it is trying to read from the latest SSTables followed by older SSTables, and the latest SSTable value is deleted, right? That's how LSM tree visualization works. We can also clear the tree and restart all over again, right? So this is the demo about LSM tree. Now let's have a look at the code. So the code structure, I've tried to keep it similar to other demos. So first we have LSM. For LSM, we have a MemTable class, which is having set, get, and clear, right? So this is happening in memory. So what are the inputs? We only have one threshold, when to flush it down to disk, right? So we have val log as our first file to be written to. So whenever we are setting something, we are writing stuff to val log. And then we are also setting the data in the MemTable itself, and we are returning the current length if it's greater or less than the threshold, right? And when we are getting, it is a simple get. We are just looking for that key in our MemTable, right? And for clear, we are clearing the write ahead log. We are also removing the write ahead log file, right? And now this is our LSM tree class. It is taking MemTable threshold and also compaction threshold, right? So we are creating a new MemTable, and then we have compaction threshold initialized. We have SSTables as an empty list, and this is what is happening on set. Whenever we are trying to set something on the MemTable, it is returning us true or false, whether to flush or not flush. If it is true, we go ahead and flush it, right? And what is happening in flush? We can see that it is creating the path for SSTable and Bloom filter. First, it is creating a Bloom filter and it is dumping all the keys that have been added so far. And then it is doing the same thing for SSTables as well, right? And then we are clearing the MemTable. So that is what is happening in set, right? And when we are deleting something, we are calling key with a tombstone value. It is simply a text called tombstone, which will be used for checking if something has been deleted in the MemTable. If it is deleted, we return null, right? Now let's look at get. So first, like I said, we are trying to look for the value in the MemTable. We are going to call the MemTable.get. If it is not available, we will try to check if it is a tombstone or not. If it is tombstone, we will return none. Otherwise, we start looking into the disk. In the disk, first we will check in the Bloom filter, right? So this whole thing is a Bloom filter check. If Bloom filter check key of 0, we just need to check the first bit if it is true or false. If it is false, we can directly return from here. If it is not false, then we go into the SSTable. This is where we get the maybe yes. We go into the SSTable and then we try to load the JSON and then we try to find the key and then return the value, right? So this is how get, and set, and delete works in MemTable, right? And this is the compaction logic. Whenever the threshold is hit during set, let me find that. Yes, here. When we are flushing the MemTable to disk, we are checking if the length of SSTables have met the compaction threshold. If it is greater, we call compact method, and compact method does similar thing. It is just merging the data from the current SSTables and then it is creating its own bloom filter. It's adding everything to itself and then removing the old table. And that's all this method is doing, right? And on the server side, it is simple APIs for set, delete, get, and clear methods. And the index.html is the UI that we have seen just now, right? It is using simple bootstrap for the styling purposes. Okay, so the code is available in GitHub, guys. Definitely check it out. If you can improve on it, I would definitely welcome it. Thank you so much for watching. If you have any doubts, definitely post it in the comments below. Please leave a like if you found this helpful. Please subscribe if you haven't done already. I will see you in the next one. Cheers.